Yeah, so it's a great pleasure to welcome Dr. Morgan Monclad, who's visiting us today. So normally you start these introductions talking about the PhD school he went to. I'm going to take one step back and point out that he went to the greatest undergraduate institution ever. That would be Bowdoin College in Maine, because that's where I went to college.
Just because you went?
Oh, because of me, obviously, and you. So after Bowdoin, he went to grad school at the University of California, Santa Cruz, and he recently got his PhD in 2016. He is now an Einstein Fellow at the Institute for Advanced Study in Princeton, and he uses computational techniques to study close encounters between stars and compact objects, and so we'll be hearing a little bit about that today. So welcome.
Thank you so much. Yeah, and it's really a pleasure to be here. I've never seen Texas A&M. I took a little jog around campus yesterday. It was great. So. Yeah, so today I want to talk about common envelope episodes, stellar mergers, sort of progress towards understanding what goes on in those events, and kind of strategies for making progress. So I think something that you're going to see is that we understand these things really kind of at a cartoon level right now, and so figuring out these stages of binary star evolution is kind of a big question mark towards understanding how you form sort of compact and merging binaries. Okay, so to start at the beginning, I mean, with single stars, we kind of have an idea of how they work, how they evolve, and there's still a lot of questions, but you know, these things go through an evolution where they have some main sequence, they expand into a giant star phase, and then they leave behind some remnants. Low mass things leave behind a white dwarf, higher mass things leave behind either a neutron star or a black hole in kind of an interesting, not necessarily monotonic way that maybe depends on the compactness of their cores. But we kind of have a pretty good idea of how this works. But what we're learning is that actually many stars are not single, but are actually in pairs. And so something like a majority of these massive stars, young stars, seem to be pairs, and some of them, like this one, are actually so close that they interact. So this is obviously a sort of artist rendering, but last year people found this sort of massive star contact binary. So the individual components are on the order of 20 solar masses each, and this seems to be a high mass analog to sort of contact binaries as we know them from eclipsing binaries. So these kind of phases of interaction are actually not kind of sort of uncommon or rare, but they might be really important in understanding how massive stars sort of live out their lives. And to give you a more specific example, let's talk for a second about, say, forming a pair of neutron stars that will eventually merge under the influence of gravitational radiation. So for that to happen, the kind of ingredients are at least two stars that are maybe 8 solar masses or more massive enough to leave a star. And if we want these things to merge, we actually have to go through some phase that draws the binary closer together, and then we have sort of a much closer pair of neutron stars. If those are something like a solar radius apart, gravitational radiation is strong enough that they'll spiral together and merge in something like a Hubble time. So if we want these things, I mean, gravity is pretty weak, right? So if we want these things to merge, they actually have to be something like a solar radius apart. And so you can immediately see that there's a problem there. You can't fit two 8 solar mass stars within one solar radius. So something has to happen to the binary orbit that kind of transforms it. And we think that transformation is a common envelope phase. So the qualitative picture of what happens here is, say we have two stars. One is evolving to the giant branch, and as it does so, it's expanding in radius, and at a certain point it kind of eats its companion. And in this case, let's say that's a neutron star, but it could be a main sequence star, it could be a black hole. And as that happens, sort of like a satellite that comes too low in the atmosphere, it gets sort of dragged down. It feels a drag force on its orbit, and as it spirals into sort of denser and denser stellar atmosphere, it goes through this kind of runaway inward spiral through the envelope. And if we're going to leave behind a binary, actually the envelope gas has to eventually get kicked out. So So I kind of think of how that might happen as being like the sort of pair of stars that start out widely separated, they drag through the orbit, and then eventually they're quite close, and if they're a strong enough kind of egg beater in the center of this big gaseous envelope, they're whipping gas around, that can kind of impinge on that gas and drive it away. And as they sort of open up a cavity around their orbit, the drag forces that were causing them to spiral together kind of disappear, and the orbit stabilizes, and you're left with a binary that's made up of the core of the giant star and whatever the secondary object is. So if we want to form this pair of neutron stars, then this core explodes as a supernova. So that's kind of one outcome. The other outcome is, if you don't get rid of the envelope, they just keep spiraling together and the pair kind of merges into a single object. And so I'd say that, I drew this as some sort of keynote cartoons, and I really kind of believe that that's the level that we understand this process at. We know that it happens in nature because we see compact binaries with separations that are much smaller than they could have had sort of on the main sequence, or even more so in their sort of pre-main sequence inflated sizes. So we know that this happens, but sort of connecting the dots and understanding the details, I think, is proved really challenging. And so there's a huge number of open questions here. And one reason for that, I think, really runs parallel to what we've seen in galaxy formation and evolution, is that if you want to kind of model this computationally, there's a huge range of timescales and there's a huge range of spatial scales. And so any kind of modeling strategy is maybe going to involve some kind of like subgrid recipes for accretion, feedback, that sort of thing. And then, just like you see in galaxy simulations, you can get into a lot of arguments whether what you're seeing is reality or what you're seeing is what you put in the model. And so this has really proved to be quite difficult. And I think it's complicated by the fact that, with one star you have one variable, the stellar mass, and maybe the metallicity, so you have a couple variables. But when you start to come up with more than one star in a sort of hierarchical system, you can come up with almost any combination of sort of properties that you want. And so simplifying that down to ask some sort of specific questions has been kind of difficult. I think, though, if we kind of had a wish list of what we want to know, there are a few general questions. And some of those are sort of about how the physics of this works, and some are about outcomes. So we'd love to know, as these pair of objects sort of get set up into in orbit, what are kind of the initial conditions that drive a pair from being kind of non-interacting to the interaction itself? So what are the initial conditions? And then as this object is spiraling through the envelope, how the both the momentum that drives the in-spiral and the energy that maybe eventually kicks out the envelope gas, how is that transfer mediated, on what time scale? And then eventually what we want to know is, say I give you some main sequence binary at a certain separation with certain masses, what will it give me at the other end? And that's the question that sort of binary population synthesis models try to answer. And they do that right now in a sort of parameterized way with our best guesses, but I think there's more questions than answers that connect the sort of before to after in these cases. So I don't know, maybe you're wondering, like, if we don't know anything, what I'm even talking about. So I want to talk about two strategies to make progress here. And I think in the best case, these will eventually converge, and they're not quite there yet, but that's the direction we're moving in. So one aspect of that is I think we need to better understand the gas dynamics that drives that orbital in-spiral. And that's set up by sort of the initial conditions for these events, and then driven by kind of the momentum and energy transfer that I was mentioning. And then I think something that's really promising is that we're starting to see events that we think are either stellar mergers or common envelope ejections in transient surveys. So I'll talk a little bit about that in the second half of the talk again. And I think really that's the way forward. And through comparing sort of hydrodynamic simulation to these events, I think we have some hope of actually sort of constraining the theoretical phase space that's been kind of vague for for the 40 years since this sort of model was proposed. So those are what I'm going to focus on in the sort of two halves of my talk. Okay, so if you don't have any questions, I'll talk a little bit about the gas dynamics. So let's imagine ourselves flying along with the object as it spirals through the envelope. And in that frame, what we see is kind of a wind of gas coming towards us. And our gravity is incredibly strong, so that gas is focused towards us. And this is kind of a Bondi-Hoyle-Littleton or Hoyle-Littleton accretion flow. And the characteristic impact parameter that we focus gas from, I'll call the accretion radius. But it's something like gm over the velocity squared. And if you look at that little expression and you switch the distance and the velocity, that looks a lot like the escape velocity. So this is sort of gas that's gravitationally bound to us as we fly through it. And that means that, you know, this wind that we're interacting with, we're focusing some gas towards us, we have sort of a characteristic cross-section that's dictated by that gravitational focus impact parameter. And this is the theory that people have kind of used to understand this in-spiral. It's probably sort of supersonic flows through the envelope, and I'll come back to that later. But that just tells you that sort of the ballistic trajectory of the gas is more important than pressure. So I think it's kind of interesting. You can see that the Hoyle and Littleton paper describing this comes from 1939. So I think it's kind of fun to actually look back at that. And you can see this diagram that looks like a mirror image of the one that I was just showing you. And what they were talking about is focusing of interstellar gas into the solar system. And they were worrying about it sort of changing Earth's climate, like would our orbit spiral in closer to the sun and like cause the climate to vary. So I think it's kind of like really fun to think that the context that we're using this work is actually really different than the context that people were thinking about it at the start. And then Hoyle actually wrote a science fiction book, which I haven't read, but is apparently kind of strange, about ISM cloud that gets focused into the solar system and like is also sentient and tries to destroy the Earth. It's called the black cloud. It's probably very strange. So anyway, this is the theory that people have used to kind of understand this in-spiral. And to apply that theory, what we need to do is kind of think about this in-spiral and the wind that's being focused towards us in kind of characteristic scales of this theory. We can rewrite this in kind of dimensionless scale. So a characteristic length scale is that gravitational focus impact parameter, how much gas is being focused towards it. Characteristic sort of time scale is the flow crossing time that material is focused towards us. And then we care about things like what's the Mach number of the gas, the ratio of our sort of orbital velocity to the second speed of the gas.
So he's clear this for something, so do you worry about shocks?
Yeah, so that's exactly what happens is you set up some bound structure. And in like 2 slides, I'll show you what some of those look like. Something that turns out to be really important that I'll talk a little bit about in the next few minutes is actually that, you know, we're not in a homogeneous sort of ISM medium, but actually we're inside of a star. And so the center of the star is really high density, the outside is really low density, and so the material being swept towards this embedded object actually spans a big range in density. So the density gradient across that focused material ends up being really important. So here I've written that down in terms of a ratio of the gravitational focusing distance, the accretion radius, to the density scale height. So that's how many e-foldings of density are there in the material that's focused towards me. Something that is perhaps obvious in hindsight, but that we're learning as we think about this more carefully is that inside of, in this sort of moments of in-spiral, the gravity that's driving the orbital motion is the same as the gravity that the stellar structure is set up against. And so the stellar envelope being in hydrostatic equilibrium, things like the pressure scale height, the sound speed, are set by the same gravity that's driving the orbital motion. So when I wrote down those sort of parameters that describe these flow, you might think, oh gosh, you have this like 4-dimensional parameter space, how are you ever going to make progress? It turns out that some of these things are related. So this is a sort of little bit nasty algebra, but simple concept. So the density scale height is related to the flow Mach number and the mass ratio of the binary. So the idea here is that, near the limb of the star, the sound speed is low because of radiative losses. The sort of pressure and density scale heights are very small, it's sort of steep gradient, and high sort of relative Mach number of the orbit relative to the sound speed. So that's one kind of flow. And then in the deep interior, the Mach number is lower, but the density gradients that are sort of focused onto the object are shallower, that sort of thing. So what we're seeing is that rather than sort of a n-dimensional phase space, there's actually some sort of like relationships here that really kind of define these interactions. And I think that's promising because it means that we can move from an infinite combination of binaries to kind of a reduced set of parameters that kind of qualitatively describe most of these objects. So the way that I'm thinking about this right now, and the illustrations that I'll show you in a few minutes are in terms of a little hydrodynamic setup that I'm calling the common envelope wind tunnel. So we're zooming along with this object, and rather than asking what sort of the full physics of this interaction are, I'm just saying, say we isolate this flow, and we set up a little wind tunnel, and just like sending kind of flow past a wing in a wind tunnel, what we're doing here is we're sending a wind of material with a profile of density, sound speed that's sort of representative of a star past a gravitating object. And so here that's a sort of point mass, and we let a material that gets too close to it accrete. So we can measure things like the accretion rate and the drag forces that this object feels in steady state with different incoming conditions. And so we can map out conditions that we think might be representative of one part of the interaction or another part of the interaction. Okay, and let me show you something about the flow structure starting from here. Okay, so what I have here is a case where there's no density gradient in the incoming flow. So this is your sort of canonical Bondi-Hoyle-Littleton flow. This is a Mach number of 2, and what we see is there's this big bow shock, and the opening angle is set by the ratio of the sound speed to the velocity. So sound waves travel this way, and the velocity goes this way, and that sets the opening angle of this Mach cone. And when I look at this, one of the most striking features to me is that for this streamline here, there's sort of an equal and opposite streamline there. And so every sort of fluid parcel focused towards this object has a sort of equal and opposite fluid parcel. And their momenta perfectly cancel in the wake. And then you see that there's material falling into the object actually sort of from this trailing edge. And so, it was a little bit rainy this morning when you ride your bike to work on a rainy day. Your front gets trenched, and that's because our sort of geometric cross-section is bigger than our gravitational cross-section, which is probably good. But this thing actually mostly accretes from behind. So 70% of the accretion is actually from behind, and that's because this gravitationally focusing material comes in, and in the wake it sort of converges and falls in. And, the characteristic sort of size here is 1 gravitational focus. So what I want to show in the next few slides is sort of kind of the effect of the density gradient on these flows and how it kind of qualitatively changes what these things look like. So if I add a density gradient, actually these are wrong, I'm sorry. So this is high density, the center of the star is down here. This is high density material and that's low density material. And what happens is that the bow shock kind of tilts to face the denser material. And rather than sort of perfect cancellation of momenta in the wake, instead you have a flow geometry where the dense material is coming in, kind of overpowering the low density material, and stuff is starting to rotate instead of falling directly into that central object. As the density gradient gets stronger, that flow structure changes even more. So we have, rather than kind of this one bow shock, we have a nested shock structure. There's sort of a leading shock and then this tail shock down here into the dense material. And actually a lot of this dense stuff is getting sort of focused around in a sort of slingshot out into the lower density regions. So I think it's kind of helpful to see this in motion. Oh, yeah, so these are actually grid calculations. Yeah, and so it changes as you go out, but the sort of finest, there's sort of a sink boundary condition in there, and that has about 10 cells across its radius, so 20 across its diameter. And then the size of the cells changes by log r, so you can like almost see some of the cells out here because we're sort of de-refining as we go. So it's sort of delta r over r is like, you know, a couple percent of the volume. So this calculation is, you know, 24 hours on 100 processors, that sort of thing. So they're cluster computing, but small for cluster computing. So they're, and really that's the motivation here, is that we can kind of survey some of the parameter space and start to ask questions about this. So this is something like 100 million CPU hour supernova calculation. And really that's kind of what appeals to me about it. Okay, so what you're seeing here is gas is coming from the left. The high density material is kind of rotating around here, and you have this kind of turbulent flow, and there's this sort of dense pile up between the material that's trying to rotate around, and the sort of constant flux of new material coming in from upstream and running into it, basically. And so at that interface, there's velocity shear, there's a density inversion, and that kind of seeds the instabilities that you see along that interface. So qualitatively, something that we're seeing is that rather than sort of falling directly in, material is trying to rotate around and then maybe getting swept downstream. So we can look at that a little bit more quantitatively also. And here I'm measuring a coefficient of drag or a coefficient of accretion. And those are normalized to the sort of Hoyle-Littleton flow values. So something like that cross section times the density times the velocity, or times the density velocity squared. So with no density gradient, the coefficient of drag is 2, and the coefficient of accretion is 0.7. I think what's important there is that they're of order 1, not those particular values. As we change the density gradient, though, and you can probably anticipate this, the coefficient of accretion changes by a factor of 100. And so accretion becomes much, much less efficient because there's sort of an angular momentum kind of barrier to material falling in. So it has net angular momentum and it rotates around rather than sort of this kind of perfectly symmetric convergence. The drag is generated by the fact that there's a wake that's higher density behind this object than there is ahead. And so just the focusing of material piles up high density wake behind, and the equal and opposite kind of reaction of that is to slow down the object. So when we measure that drag force, we see that it sort of changes mildly across different density gradients, but it's not nearly as strongly effective as the accretion rate. And you can kind of understand that by the fact that material is sort of focused into that region and gravitationally interacts with this in-spiraling star regardless of whether it accretes, but it doesn't necessarily make it down to the object itself. Okay, so to sort of make this a little bit more specific, let me think for a second about integrating a black hole spiral through a couple of envelope episodes. So you all heard last year we discovered these merging black holes with LIGO. Something remarkable about that discovery is that those things were like 30 solar masses each, added up to a 62 solar mass black hole. And I think that ran sort of contrary to many people's expectations. So something you could ask is, oh, did it gain a sort of a huge amount of mass at some point during its evolution? Did it start at 10 and end up 30? And one of the sort of prime candidates is actually this sort of phase envelope interaction. If you ask, when is there a lot of dense gas around the object, this is really one of those phases. So here, if we want to understand how the object spirals in, we can use the results of our calculation there, and we just say the change in sort of orbital energy comes from that drag force, and it's some coefficient multiplied by the sort of Bondi-Hoyle-Littleton drag value. And the change in mass is some coefficient of mass accretion multiplied by the Bondi-Hoyle-Littleton value. And then we put those coefficients in, and what we get is kind of interesting, I think, at least. So the first thing is, hopefully you can see this, and I don't need you to get every detail out of this, but just qualitatively, the blue line shows if I use a coefficient drag of 1 everywhere, and the pink shows if I use the results interpolated from our latest simulations. And what you see is that just kind of qualitatively, the orbit is a little bit different. So with the interpolated coefficients, the initial in-spiral is a little bit more rapid. But even more important, the mass gain is really dramatically different. So with coefficients of 1, which I showed you are about right for sort of normal homogeneous flow towards an object, the change in mass of the in-spiraling object is something like the reduced mass of the envelope and the object itself. So it gains a mass sort of order its own mass. That means if I start with a 10 solar mass black hole, I end up with a 20 solar mass black hole. And maybe you think, oh, that could be good. But it also means that if I start with a 1.4 solar mass neutron star, I end up with a 2.8 solar mass black hole, and all of a sudden that gets us into trouble because we see double neutron stars in binaries, like the Hulse-Taylor binary pulsar, and they have masses that are really close to 1.35 solar masses, and they have this really narrow dispersion. So these things can't have gained that much mass. And it seems like part of the answer is just the geometry of the flow. So if we use realistic coefficients of drag and accretion, we get that these objects gain at most a few percent of their own mass during kind of their orbital in-spiral. So there might be slight differences in the kind of the trajectory of the spiral itself, but there's big differences in kind of the mass gain by an object that's going through this process. And the upshot of that is that we don't really expect these things to gain a lot of mass during their in-spiral. For black holes, we don't expect their spin to change a lot from mass accretion during this in-spiral. So if black holes gained a lot of mass, we'd expect all the LIGO sources would have spin 1. And so far, the one we have a spin constraint on is inconsistent with that. So maybe this tells us that this phase isn't important for mass accretion. Okay. So some of the work that I'm doing right now, just to wrap up here, is thinking about. I showed you isolating sort of one parameter in that space, the density gradient. And here I'm thinking a little bit about what if you sort of vary all the parameters that should be varied in unison? How do these flows qualitatively change? So this case is a very steep density gradient, but also high Mach number. So it's like we're at the stellar limb, the Mach number is high, the gradient is steep, and the secondary star is racing along. Get this very distorted And then this one in the upper left is a lower Mach number, shallower gradient, so it's like we're deep in the envelope. And I'm looking at, again, these sort of coefficients of mass accretion, drag force, which drives the orbital transformation, so the transformation of the object, the orbit. And the last thing that we care about is the sort of coefficients of energy deposition into the envelope gas. And so that starts to tell us something about how the possible ejection of that gas is mediated. So you can ask me more questions about this, but I think just sort of qualitatively we're trying to sort of move towards a more and more realistic understanding of how these things sort of co-vary with each other and carve out sort of a line in that parameter space. So let me know if you have questions, or the next thing I want to talk about is sort of catching these events in action and what we see in transient surveys. So I think the goal here is really, we can, you give computational people or theoretical people the freedom of having no observations, and you can come up with 1,000 models for one process. And I think that's a huge problem because there's nothing to differentiate this. And so I think this is a good time to be going back to basics and kind of analyzing some of these flow properties exactly because we're starting to get direct constraints on them. So what I'll show you here is some evidence from transients that we have, and then as I close, I'm going to try to sort of tell you about what I think the steps are to let those processes converge. Okay, so catching these events in action, how do we do that? The idea is that as one object kind of plunges inside of the other, that's not a gentle process, that's probably sort of violent to some degree. There are shocks in the gas, and it ejects a little bit of gas. And as that gas expands, it eventually becomes transparent and it radiates, and we see some sort of optical transient. So I think a really kind of definitive object for this class of transients was this event B1309 Scorpius in something like 2008.
Why is it in German?
I really like this picture, except for the fact that it's in German. I mean, well, not that I'm opposed to German, but that it's a little confusing. So, this picture, and the reason I like it is the fact that it shows that we saw this optical transient, something like 10 magnitude flare, and folks actually looked back and saw the star in the OGLE data set. So there's I-band imaging over about 8 years beforehand, and what they saw is an eclipsing binary. And so there was a binary star before, and then afterwards they saw a single star. The binary star wasn't just a binary, but actually had a decreasing orbital period. So I think this was really strong evidence that we were starting with a binary, there was some blip, and then we were coming out the other end with a single star. So this class of objects ended up being called luminous red novae. There's sort of a low-budget band in San Francisco called Luminous Red Nova. At a certain point, they had stickers. I was hoping I could order one. Didn't work out. But so anyway, okay, we don't like them. It's not that. But these are actually, this is kind of a wonderful plot that shows all the transients we can think of, their characteristic timescale versus the peak luminosity. So classical novae live down here. They're not very bright. They have a big range of timescales. Supernovae live up here, and these objects kind of live in this in-between. And so they're more luminous than novae. They're redder in color, and so they ended up luminous red novae. But I think we're now learning that many of them are actually sort of stellar mergers. And so we have these one or two really conclusive events, and then the rest are kind of spectroscopically and photometrically inferred to be that same class of transients. So let me talk about one event in some detail, and then come back to the big picture. So in the Andromeda Galaxy, right over here, in January 2015, there was this really interesting event. So you can see it there. It was detected by the master network. And people followed it up because they thought it was a classical novae in M31. And what makes this really interesting, and turned out to be one of these luminous red novae instead. And I think what makes this object special is that there's HST imaging of this spot about a decade before. And so all of a sudden we have a connection between the star beforehand and the outburst that it drove. And so we can try to see what we can learn from that connection between sort of the binary system before and the outburst itself. This is, I told you about that object E1309 Scorpius. I think that sort of association was made more complicated in that case because we had only one band of imaging before, so we didn't have color. And we didn't know the distance. So here, this being extragalactic, we know exactly how far away it is. And we have this really nice HST imaging and detection, the pre-outburst source. So the light curve of the outburst looks something like this. So these B, V, R, I. And these are called red novae because here you can see these color bands are dispersing. It's becoming redder and redder with time as it goes along. And the spectra, I think, are interesting also. So early on, there's very broad H-alpha emission, a full width half maximum of something like 400 kilometers per second once you take out the deconvolve the instrumental resolution. And so the step that I took with these data was to look at what you can infer if you just imagine the emitting surface is a black box. So that's kind of simple. You have some color. From a color, you can go to an effective temperature. So this thing is sort of thousands of Kelvin at the photosphere, and it becomes sort of bluer and then fades away, and it has a long kind of tail where it's sort of a few thousand Kelvin effective temperature. So then you can sort of reconstruct the bolometric luminosity because we know the distance and the sort of radius of the photosphere that you would need to give you that luminosity. So in terms of the light curve, I'll come back to this in a second, but you see kind of two bumps there. So there's an early peak and then a later, longer peak. And the photosphere, what we see is that it at first expands as these sort of optically thick ejecta are expanding. And then it starts to contract again. And I think what we're seeing there is that we're looking deeper into the ejecta. It's not that the gas itself has turned around and is falling back. It's that it's always expanding, but it's becoming transparent, and we're looking deeper into the remnant. Okay. So this light curve, there's this sort of peak portion. And if we kind of think about this a lot like a type 2p supernova, so these are one supernovae with a lot of hydrogen-rich ejecta that have kind of a plateau in their light curve. We can model this sort of peak portion. It gets as just being kind of some gas that's ejected, and heat is diffusing through that gas, and so we see a peak in brightness at a time scale that's comparable to that heat diffusion time. So if we inject a lot of heat, we sort of heat up this gas, and they throw out some amount of mass, and we just ask, when does that shell become transparent? When can we see that heat? We can sort of model that phase, and you find that there's sort of something like 1/100th of a solar mass is compatible with the luminosity and time scale of that peak. And then there's this sort of what I call the plateau phase, and this is hydrogen-rich ejecta, and if we look at that sort of temperature stabilization, it seems like what's happening is ionized hydrogen is recombining. And as it does, the opacity changes a huge amount. So you go from sort of like Thomson opacity to much, much lower. And so as that gas recombines, it sort of dictates the position of the photosphere. And that's what we see in type 2p supernovas. So the plateau phase, the P, is a sort of recombination way of sweeping through the ejecta. And so you can use all the work that's been done on type 2p supernova to kind of understand the mass content of that portion of the light curve, and it's something like 0.3 solar masses. Okay, so there's these sort of portions of the light curve. They're total of a few tenths of a solar mass in the ejecta. And what's really interesting is we can compare that to the star beforehand. And if we go through that exercise, we don't exactly know the reddening to the source, so there's a little bit of uncertainty here in the exact magnitude and color. But we can kind of infer the properties of the star. And so what we learn is that it's, as a function of reddening, it's, a few solar mass star, maybe 4 to 5 solar masses. It has a radius of about 35 solar radii, and an escape velocity of a couple hundred kilometers per second, so 200 kilometers per second escape velocity. Okay, so the first thing we realize is that the ejecta mass, a few tenths of a solar mass, is much less than the mass of the star. So this object isn't being sort of completely destroyed. So we have 4 to 5 solar mass, 30 solar radius star. You can ask what the orbital period of, say, like a test mass around the surface of that star is, and it's about 8 or 10 days. And so something kind of remarkable is that this transient rises to its peak brightness in a time that's comparable to that orbital period. And so I think that's sort of fascinating because we have a binary that's lived sort of millions to hundreds of millions of years sort of with this pair of stars, and somehow in one orbit something really goes wrong and it causes this outburst. And so we have to ask ourselves what makes that so sudden. Additional evidence that we have is that the ejecta are kind of a factor of 2 above the escape velocity, so they're sort of fast ejecta. This isn't a gentle process. And the ejecta mass is kind of a fraction of the total mass. And so this is some process that in a sort of rapid timescale compared to the orbital period ejects a small amount of the mass pretty quickly. And so I think it's an open question what sort of evolutionary scenario leading up to the interaction gives us that sudden of a runaway, basically. So I've been thinking a little bit about that. One possibility is that if the pair of stars is desynchronized in the sense that if the envelope isn't co-rotating with the binary, then one star is kind of, the secondary star is kind of skimming along the surface of the primary star. And it's focusing material towards itself like we sort of saw in those wind tunnel calculations. And if you look kind of in the global scale, what happens with that focused material is it gets a sort of slingshot around and it gets ejected out. And what we find is that that ejecta is sort of raises kind of a few percent of the mass to velocities sort of at or above the escape velocity. So qualitatively, that seems kind of consistent with what we're seeing. And so maybe these sort of luminous transients come from cases where the binary, rather than being kind of synchronized and going through this kind of gentle Roche-Loeb overflow process, is actually not synchronized and is kind of in this almost like vegetable peeler mode, shooting off ejecta at kind of high velocity instead. I think that remains uncertain, and I think one of the steps towards answering this more conclusively is to look at sort of across a range of synchronicity, how the ejecta sort of depend on the binary initial conditions, and so that's sort of work to be done. But I think there's promise for this sort of approach of comparing the kinematics of the ejecta to the initial conditions, and then what we really want to do is kind of synthesize what we think the emergent light curve would be, and directly compare that to the observation. So that object that I just told you about in M31 was in January 2015. In February 2015, there was another one in M101. And I promise I won't go through every month between now and then with another object, but I think this one is interesting to reflect on because it's actually different in a number of ways. And so what you see is marked here is the position of the progenitor in STSS imaging, and you see it's in this kind of knot of star formation in one of the spiral arms of M101. And here's the sort of multi-band light curve of the transient. And we actually missed the peak of the light curve because the object was behind the sun, but when people looked back, it was sort of fading in the optical and still quite luminous in the infrared. So these are infrared bands, these are optical bands, and that sort of widening is that reddening of the ejecta that we saw before. And so the portion on the left there is the sort of pre-outburst source in all of these sort of SDSS, CFHT imaging that we have because this is kind of in a nearby bright galaxy. Okay, so you can do sort of a similar exercise and ask what the properties of this source are both before the outburst and during it. So before the outburst, we have something like an effective temperature of maybe 7,000 Kelvin, a size of about 200 solar radii. This seems like something like an 1819 solar mass giant. So this is evolved off the main sequence, and it's a giant star. And I think it's interesting that this is so much more massive than the event in M31. And so these transients seem to be probing a pretty wide range of stellar mass. From the spectra, the ejecta mass is something like 500 kilometers per second, and we can look at the radius evolution and temperature evolution over time. So again, the temperature evolution fades to a few thousand Kelvin. The radius of the photosphere that you infer here is much more kind of interesting evolution than in the M31 event, so there's some sort of peaks and troughs. Maybe that's either some sort of line of sight effect through kind of geometrically complex ejecta. I think that's easy to imagine. Or you could have kind of multiple sort of episodes of outbursting. Okay, so here's the bolometric light curve that you infer. And I want to draw your attention to sort of one feature of this, is that this plateau that we think is a recombination wave going through the gas is much longer duration, so it's a few hundred days. And if you apply those scalings and ask how much mass we're talking about there, and you put in that time scale of the plateau, then you get an ejecta mass of something like 10 solar masses. So, do we know that with certainty? I'd say no, because you'll notice the powers on some of these scalings are pretty high. So, and we don't have a ton of data points there. So, but this is something like 1 to 10 solar masses of ejecta. And if it's on the 10 solar mass end, then I think this is really, really exciting because we're seeing an ejection of an amount of mass that's kind of comparable to the mass of the envelope here. So we're seeing maybe where I had that cartoon of the bifurcation between mergers and common envelope ejection. It's possible that this one looks consistent with ejecting a large fraction of the envelope in this kind of dynamical time scale. So stepping back a little bit, if I apply those same scalings to a range of objects, the first thing to notice is that these are a few of the best studied of these class of transients. They have a range of stellar masses from around 1 to around 30 solar masses. These are all kind of photometrically and spectroscopically similar. And if we try to infer the ejecta mass, I'd say there's sort of much bigger uncertainty in this column than in this column. But we also get a range of values from a few hundredths of a solar mass, and this was a galactic transient. And then all these are extragalactic transients of kind of increasing luminosity in this direction. Then we get a range of values from something like percent of the total binary mass to some sort of order the binary mass. And so it's possible, but I don't think we know yet that we're seeing the continuum between sort of merger events and envelope rejection events. So I think this is a really promising way forward, and especially these extragalactic transients seem to be really useful because we see the sort of progenitor star before, and we know the distance, and sort of by analogy to supernova work, it's sort of can be more useful than even seeing brighter, closer events in our galaxy. So this object V1309 Scorpius went through its outburst in 2008. What's it doing now? Something that we see is that the SED is, so here's optical, is really kind of strongly infrared dominated. So the ejecta here seem to have formed dust, and that dust is reprocessing light from sort of bluish light from the central source into the infrared. And so if we look at the bolometric light curve, what you infer from the optical only is these orange stars that sort of dramatic fade away over the kind of years after the outburst. And that was the status until this year, and I think it was puzzling because on some level, you don't expect the thermal evolution of a star to happen on a time scale of 1 year. Stars do everything so much more slowly, but here we're seeing that maybe a lot of that is processing. So there's been some fade after the outburst, but we're seeing kind of a slower fade of the total luminosity. So I think it will be really interesting to continue to follow these objects, and in particular, I don't know what the best strategy is, but I think we need to think about how to best sort of see through this dust and analyze the central sources and see whether we can determine whether there's a binary there or whether there's a single star there. Okay, so with all of this in mind, what have we kind of learned about common envelope episodes, stellar mergers? I think the most striking thing is that stars are in binaries. They sometimes swallow other stars. And if nothing else, I hope I've convinced you that we have no idea how the details work, basically. We know this happens. We know that it leads to the formation of compact binaries. So we know in some cases they merge, and in some cases they eject the envelope. But I think catching these events in action and kind of in this era of time domain astronomy is the way forward, basically, because we can actually constrain things like the ejected mass. We can ask how it compares to the mass of the binary. We can look at the kinematics of that through the spectra. And just to kind of close, as we start to discover more and more binaries in the kind of gravitational wave domain, I think this is a great time to be asking these questions because we want to understand the assembly of those sources. So to assemble those gravitational wave sources, we know we had to have passed through episodes like this. So let's sort of add value to those data by understanding the history of those objects. How do we end up with 230 solar mass black holes merging, not just the fact that we have them. So thanks so much for your attention, and I'll be happy to ask or answer any questions if I can.
Questions?
I'm just wondering, perhaps making things way more complicated. So if you have a compact object orbiting in this common envelope and it's accreting material, fusion is going to start to occur on a shell around it, right?
Sorry, what? Fusion? Yeah.
And that could be that's a huge energy source, actually.
Yeah. And so that's I think a really insightful point. And so let me go back to so first of all, I agree, and then let me go back to the biggest picture. And so the way that binary population synthesis codes try to map an initial condition to an outcome is through kind of an energy equation balance. And that energy equation says the orbital energy is my source term, and the envelope sort of gas is my only sink term. So how much do I have to change the orbit to get rid of the envelope is the way that works. And so I think what you're picking up on correctly is that there's more sources and sinks, basically, in that energy balance equation. And there's sort of potentially a feedback from accretion, either through nuclear heating or like winds from a nuclear-dominated disk around a compact object. And if those start coupling with the gas efficiently, I think it'll be really interesting to ask how that affects the outcome. So I don't know, in every other accreting compact object system, we see flow structures that kind of form disks, launch jets, that sort of thing. And so I think it'll be interesting to see how those impinge on these envelopes. So the strategy that we're taking for that is, you can't simulate both of those things, sort of the global scale and the local scale simultaneously. So to give you a sense of that, the sort of accreting boundary condition I had in my wind tunnel calculations, if you undo the dimensionless scaling, is something like a solar radius. So there's still a long way for gas to go from a solar radius down to like a few kilometer black hole scale. So I think the way forward is maybe to kind of inject that feedback on a sort of subgrid type way. And so we're thinking about doing that in SPH calculations, where you kind of have like models for black hole feedback from galaxy evolution simulations, and tagging along with that methodology. So I think that won't answer all the questions you'd love to ask, basically, about the details of the microphysics of that flow. But it'll sort of ask the broad question of, is that dynamically important or not? But yeah, I think that's a great point.
Oh, actually, so your showering is like feeding sequence or
I'm talking around the compact object itself, as it's accreting material from.
Yeah, so it gets so hot that basically you probably have shells that you go like hydrogen to helium.
Yeah. So
all the way up.
Okay, this is surrounding the
Mm-hmm.
Yeah, okay.
Mm-hmm. And so at some radii in the disk, if you imagine kind of like a disk-like inflow, that nuclear energy generation would be sort of similar to or larger than the binding energy. So it's not clear that gas can like make it through those shells. So yeah, I think that's really interesting.
Gotcha.
So you did a great job of explaining what we think happens, if we happen to find one of the observations of these binary star system.
Yeah.
My question about all of this work, the LIGO results, everything is, do we have a good enough, do we have any kind of picture of stellar evolution or stellar star formation to be able to explain how or why we would be able to find one of these binary systems?
Yeah, so I think the trouble for LIGO has not been that these things exist, but to understand like how frequently they exist. And so basically I think LIGO will answer that question, but the reason why it was sort of years and years of like pushing down limits was that the difference between kind of the optimistic binary population synthesis calculations and the pessimistic is a factor of 1,000. And that all comes back to the details of how this works. So those ingredients are kind of embedded as parameters there that we don't know to a factor of 100. And that affects things like how frequently say I have a pair of objects, how frequently do they merge versus how frequently do they eject the envelope, and what's the orbital separation that divides those two. And so I think here I think what we're hoping to learn is not so much like whether we're surprised that this is happening, but like how frequently it happens, and does it happen across all masses of stars, or is there something special? Like, do you need extra ingredients to drive envelope ejection in certain cases, like in massive stars? I think it'll be really interesting to see whether sort of the rates of events line up with kind of the simplest expectations, or whether we need to invoke something. And so to me, that's where the biggest questions are. But But I mean, I think there's big questions in, you know, even just like, how do two stars co-evolve up to the point of these. So, yeah, I think you're right to identify that there's questions at all stages along this kind of pipeline. Yeah.
Yeah, will LSST find a lot more of these, or are the nearby galaxies already being covered enough that we?
No, so I think it will by going much deeper, basically. And so, like, you know, like any other class of transient, we'll be seeing these. We won't be finding tons more probably in the local few galaxies, but we'll be finding a lot more extragalactic sources, I expect. And so I think the challenge for the future is how to best use those data without sort of follow-up spectroscopy on all of them. What can and sort of develop models that let us learn as much as we can from the photometry alone. I think that'll be a huge challenge for LSST science here, particularly where we don't quite even know what we're looking for. So we've identified a class of objects that we think are this sort of transient. It's not clear if there are others that look different. Are there sources that are IR bright instead of optically bright? We just don't know. So hopefully quantity will let us ask that question, and detailed follow-up on a few sources I think will be essential while we still don't know what we're talking about.
Okay, was there anything else? No.
Well, thank you so much.
Thank you.